I promised to give a negative result about why measure theory and probability theory don't work when you work with the power set in general. And I think it's a good time to make this remark here, since we were already talking about the Lebesgue measure. Remark. There is no measure on the real line with its power set such that the measure of an interval equals its length. That's why we said the power set is too big to work with in general. This is the important part. It doesn't work with the power set. Again, this is a deep result. It's a deep result, and we're not going to discuss the proof or anything. But at least this should be a motivation, an argument to use sigma algebras that are, in general, smaller than the full power set. Okay? You cannot construct Lebesgue measure on the power set. That's a negative result. Okay. Okay, now maybe another example of a measure in a that is not necessarily a probability measure. And I'm going to put it right here, just next to Dirac measure, related to your question. Okay, so that's an example of a measure, okay? So you have omega f, measurable space, and D, countable subset. Let's say D is omega 1, omega 2, etc. Also works for finite D. But I'm just going to fix my notation for this. Okay? Here's what we're going to do. So instead of fixing one point, we're fixing a lot of points, countably many points. Omega 1, omega 2, omega 3, etc. And assign a mass, m1 kilograms of gold, m2 kilograms of gold, m3 kilograms of gold. Of course, those mi's are positive for each I. But they don't have to add up to 1 because we're not discussing a probability measure now. This is just going to be a measure. Okay? So the problem is, can we measure the amount of gold that we cover in our field? What is our field? Well, we just determine it based on what is assigned to us as a field. So let's say this is our field, our event. So the probability of an arbitrary event so probability of A is, not probability, sorry. The measure of A is amount of gold covered in the region A. So how am I going to define it? Well, I want M1 or Mi if the point where Mi is standing is covered in my region. How can I check if omega 1 is in my region? Well, I can look at my Dirac measure. Dirac measure is just checking if omega is in my region. So let me multiply this mass with the Dirac measure at omega I and sum it over all i's. So in the purple example, the purple set A, so the measure of A is what? M1 plus M2. Let me draw another. The measure of B is 0. Sorry, we couldn't find any gold. So that's what you get, 0. Again, so this is for every A in F. And check that mu is a measure. It's called the discrete measure associated with the set D and masses M1, Mi, etc. And even one more remark, maybe here. So, remark. So if omega is countable, then every measure on omega F can be written in this form. Well, if you have only countably many points, you can just see those points as your fixed points, and the probabilities or the masses assigned to those points are just the amount of gold assigned to each point. So if you don't have any part of the region that is not covered by a countable set D, then every measure on a countable set omega must have this specific form. So if you have a discrete set, a countable set, a measure is a discrete measure, and it has such a formula. And let me also say a special case. If the sum of mi's is 1, then the measure of the full set is all i's, which is 1, so that mu is indeed a probability measure. So in particular, the uniform measure on a finite set, also the binomial measure on the coin tossing space, and the Poisson measure on Z plus are discrete measures. So the examples that we discussed in the first hour, they are all in this form. And even one more special case. just take M1, M2, etc. being 1. This means mu A is just sum of the Dirac measures, 1 at A, 2 at A, 3 at A, etc. Just sum, if this is 1 for every I, then this is just sum of Dirac measures. In other words, there is only 1 kilogram of gold at each point. So what does it do in this case? What does the measure do in this case? If it's just saying, if it's just sum of bunch of Dirac measure, what does it count here? What does it give you here? So this is saying 1 if omega 1 is in A. This is saying 1 if omega 2 is in A, etc., etc. What do you get when you add those numbers? Total number of points, actually, right? Total number of points covered in A. So in this case, it's called, mu is called the counting measure. The counting measure associated with D. So we already have a bunch of examples of measures, right? So we started with the simpler Dirac measure. If you have sum of Dirac measures at different points, you get accounting measures associated with those points, set of those points, okay? Which is just counting the number of points covered in your area, in your region. And they are all part of this general notion of a discrete measure, which can be defined on an arbitrary measurable space. Okay. Any questions so far? Okay. So maybe we should prove some properties of measures, some elementary properties of measures. Remember last time we proved only 2 or 3 properties of a probability measure on top of its definition. So now we're going to prove more properties, but for arbitrary measures. But they of course, hold for probability measures, OK? So, OK, maybe proposition. So let's say we have a measure space. What does that mean? Omega is a non-empty set. F is a sigma algebra. Mu is a measure. Mu is a measure means what? Mu of empty set is 0, and mu is countably additive. So if it's countably additive, it should also be finitely additive. So mu is finitely additive. So this means if you have A1 to AN that are disjoint, then mu of the union is sum of the individual measures. And so for the case of probability measures, we already checked this. So I don't want to repeat the same type of proof. Checked for probability measures. Same proof applies. So we just skip it. Monotonicity. Okay, mu is monotone. So this means if you have A, B that are events, and A is a subset of P, then the measure assigned to A is less than the measure assigned to B. So let's draw a picture. It's going to be easier this way. So A is here, B is here. Okay. So, and of course, the idea is to use the previous property, A, right? Finitely additive, being finitely additive, or finite additivity. How can we use it? You need disjoint sets, but A is included in B. How can you create disjoint sets out of A and B? B minus A, right? So you can see B as A union B minus A, and these two are disjoint, as observed in the picture. Right? So therefore, we can apply part A but this is a non-negative number, so this is greater than mu A. So this is mu A less than mu B. And let me add one more property. So let's say you have AB and again, A is a subset of B, but B also has finite measure. Then the conclusion is that mu B minus A is mu B minus mu A. I just wanted to state it separately. It doesn't even need a proof because that's the same thing as in part B. We have this equation, right? And if this is finite, then this is also finite. So you can by this star, this follows directly. Okay. So this is like okay. So this is just another way of writing this star equation, right? Okay. Sequential continuity properties. So mu is sequentially continuous under increasing limits. Here's what we mean by this. So if we have A1, A2, etc., all in F, then the union, the measure assigned to the union of those sets is the limit of the, let me write this way, is the limit of mu ANs. So on a picture, again, this is very nice. So A1, A2, A3, etc., and we have omega. Okay? So if you look at the result, and if you look at the picture, we already know that probability or measure is monotone. A measure is monotone, right? So this is a subset of A2, therefore A2 has a larger measure. This is a subset of A3, therefore A3 has a larger measure. So we're getting a larger and larger number. And if you have such an increasing sequence of numbers, they're going to either converge to a finite point or they're going to explode to plus infinity. So the limit always exists as a number in 0 to plus infinity included. So let me first say by monotonicity, which is B, we have mu A1 less than mu A2, etc., so that the limit of mu A n's exists as a number in 0 to plus infinity included. So it is either converging to a finite number or it diverges to infinity plus infinity, okay? Because of this monotonicity, this is always the case. But why should we have this limit equal to mu of the union? That's the question. Why do we have equality here? Well, again, the idea is to break the problem into disjoint sets. You are given not necessarily disjoint sets, well, not disjoint sets at all, because one is inside the other. So you can come up with a way to create disjoint sets, and it is not very difficult, because it is already here, right? Call it B1, call the remaining part of A2 in A1, A2 from A1, call it B2, call this B3, etc. So let's set B1 to be A1, B2 to be A2 minus A1, B3 to be A3 minus A2, etc. And each of them is in F, because these are sets in F, and sigma algebras are closed under set operations that are finitely or countably many. So the point about these is that B1, B2, B3 are disjoint sets. And we can write Bn as, we can write An as B1 union B2 up to Bn, right? A3 is B1, B2, and B3 together. So I can even write mu An as mu B1 to mu Bn. Okay? So what was I interested in? I was interested in this limit. So n goes to infinity mu An is n goes to infinity of this expression mu B1 to mu Bn. So this is limit of n goes to infinity I from 1 to n mu Bi's. But by its definition, this just means infinite series, 1 to infinity. So disjoint sets, mu Bi's, 1 to infinity, disjoint sets. So this is already from the definition of a measure is equal to mu of union of Bi's. Definition of measure. Because Bi's are disjoint. And what is the union of Bi's? Union of Ai's. So you can either take it a union like A1, now A2, A3, A4, etc., or you can say, hey, B1, now add the B2 part, now add the B3 part, you will get the same union. These two are the same sets. And this finishes the proof because this is what we wanted to show. There is a reverse property. First of all, any questions about sequential continuity under increasing limits? So that's an important property, okay? When we need to take limits, you're going to need to use this property a lot. And there is a reverse counterpart of this. Mu is, let me first say, suppose mu is finite. Mu is finite. That is, mu of the full set is finite. Then mu is sequentially continuous under decreasing limits. So this means what? Well, if you have A1, A2, A3, etc., now in the reverse order, all in F, then now you have A1, A2 is smaller, A3 is smaller, so you should intersect them. The measure of the intersection is, again, the limit of the individuals. Okay. So let me again draw a picture for this. So this is omega. You have A1, A2, A3, dot, dot, dot. Maybe there is some intersection here. Intersection. So we're interested in the measure of this intersection. Well, you can either try a direct proof like here, or you can save some time by using this result. Because this was in increasing order, now this is in decreasing order. Can you make those sets, can you revert those sets in a way to get an increasing sequence of sets? So if these are sets that are getting smaller and smaller, what are the sets that are getting larger and larger? They're complements, yeah. So let Bn be an complement, right? So B1 is smallest, B2 is bigger, B3 is even bigger, et cetera, et cetera. And by the previous property, we have that mu of the union of BI's is the limit of mu BN's. Well, what is the union of BI's? Can you compare it with the union, intersection of AI's? What's the relationship between the union of BI's and intersection of AI's? Remember, BI is complement of AI. What's the relationship between those two sets? Union of BI's, what's the complement? Intersection of BI complements, which are AI's, right? So these two are their unions. Therefore, we have a result about complements. Well, maybe here, right? You can just take the full set here by C. So by C, we can write this as mu of omega minus mu of this intersection. And you can write this as mu of omega minus the limit of mu B, mu AI's, AN's. And since these are finite numbers, just gone, and we're done with the proof. So these are simple properties that are very useful in calculations that we're going to do later. So you should know them. And there are just last two properties. So we all talked about countable additivity where we have disjoint sets. So what do we do when we have not necessarily disjoint sets? Okay? So this is called Boole's inequality. Boole's inequality. Finite case. Finite case. So this means if you have A1, A2, etc., AN, finitely many sets, not disjoint, but they're just events in F, then the measure of the union is less than the sum of the individual measures. Okay, so this is called Boole's inequality. And I'm going to do the proof for n equals 2. Generalize by induction is an exercise. Okay, when n equals 2, it's very easy to see. So we're interested in A union B, right? Let's say just two events, A and B, not necessarily disjoint. Well, you can see it as mu A plus mu B minus A, as we did in this star equation, where the union was actually B anyway. So let me draw a picture. So A and B, okay. So here's A, and here's B minus A. So therefore, they are disjoint. And this itself is a subset of B. Therefore, this is less than mu B by monotonicity. Okay. And there's an infinite version of this. So Boole's inequality countable case. So if you have A1, A2, etc. in F, then the measure of their union is less than the measure of the sum of the individual measures. This is also sometimes called countable subadditivity instead of Boole's inequality. If you don't remember the name, Boole, this is also more informative title for this result, right? Countable subadditivity, not equality, but just inequality, because sets are not disjoint. Sets are not disjoint, and I'm going to leave the proof for you. Just extend the finite case to the infinite case by taking a bunch of limits, okay? And this brings us to an end of results, basic properties for measures. But we haven't answered the question of defining measures on uncountable sets yet. Okay? So our last question today to discuss is specification of measures. So it is still open how to easily define, or let me say specify, measures. So there comes the important theorem about specification of measures. So let omega f be a measurable space, and mu and nu, two measures on it. And also let P, script P, be a pi system generating F, meaning that sigma of pi is F. So we are going back to monotone class theorem, it sounds like, right? So part A. So suppose mu of omega and nu of omega are the same, and suppose mu and nu coincide on P. That is, mu of A equals nu of A for all A in P. So you have two measures. You want to check if they're equal on the whole sigma algebra. The theorem says it is enough to check if they're equal on a pi system that generates this whole sigma algebra. So here's the claim. Then they also coincide on F. That is, mu of A equals nu of A for all A in F. Part B, well, I forgot to write, it is finite, okay? It's finite. So part B, suppose omega has a countable, measurable partition. Omega 1, omega 2, etc., such that mu of omega I is equal to nu of omega I for all I. If mu and nu coincide on P, then they also coincide on F. Same statement, but for the sigma finite case. Same statement for the sigma finite case. Let's first look at A. B is an extension of it, so let's focus on A. And I also forgot to put less than plus infinity, sorry. Plus infinity for all I. Okay? So one is for finite measures, the other is for sigma finite measures. Okay? So let's hope that if we can do the finite case, we can also do it for the sigma finite case. Okay. Here's the proof of A again. Let's prove A and leave B as an exercise. The main idea is in A. That's why. Okay? So here's what we are given. Mu A equals nu A for all A in P. I have two measures. They happen to assign the same measures to events in a pi system. Think about one of the pi systems that generate the Borel sigma algebra. Let's say intervals A to B. Okay? You have two measures, mu and nu, for which the measures are the same for all intervals A to B. Mu of A to B equals nu of A to B. The conclusion will be that mu of A is equal to nu of A no matter what A is. This is true for every A in the whole Borel sigma algebra. Okay? That's what we're trying to prove. And that's why we fixed a pi system that generates the sigma algebra. So what are we going to do? Idea is to use monotone class theorem to pass from P to sigma P, which is F. So let's use this idea. Define a collection of sets for which this property holds. That's a natural definition of the Dynkin system that we're looking for. Why? Because automatically this contains the pi system P. Automatically, P contains D. Exercise, show D is a Dynkin system. Then, by theorem, done. This, because we have this implies this, and this is F. So we conclude mu of A or mu of B is equal to mu of B for all B in F. That's the magic done by the monotone class theorem. So all you have to do is to see how you should define your Dynkin system. Once you come up with the idea of the definition of your Dynkin system, the rest is easy. The difficult part is to come up with this idea. But the hypothesis of the theorem already gives you a hint. You have a property that holds on a pi system. So why don't we just extend this pi system to a larger class of sets? And this is going to be this Dynkin system. Show that this is a Dynkin system, and then use monotone class theorem to say that, well, this Dynkin system also contains the sigma algebra generated by the pi system. And this is our whole sigma algebra F. So we proved it. We proved it up to some details. You need to check this is a Dynkin system, but it's a routine exercise in the sense that you just look at the definition of a Dynkin system, number 1, number 2, number 3, and you check them one by one. Okay? That's why I skip it. So, some remarks. This theorem especially part B, proves the uniqueness of the Lebesgue measure on R. Why? So let's say it's not unique, okay? Let's say there is another measure, Leb tilde, on the real line with the Borel sigma algebra, for which the Leb tilde of the interval a to b is b minus a for all ab. Well, this is already Lebesgue of a to b. So if you have another measure, like the Lebesgue measure, which assigns to an interval its length, then you have your mu and nu. They coincide on intervals. Intervals form a pi system. Therefore, they must coincide on the whole Borel sigma algebra, because this pi system consisting of intervals generate the whole Borel sigma algebra. Since this is a pi system generating the Borel sigma algebra, we must have Lebesgue equals Lebesgue tilde, meaning that the Lebesgue measure and the Lebesgue tilde measure at every Borel set is the same. And before we go, even one more result, one more thing, and we're going to be done. We're going to be done with the measures. Okay. So do you remember the idea of tracing? You have a big set, a sigma algebra, a smaller set. You can create a sigma algebra on that smaller set. How can you create a measure on the smaller set if you are given a measure on the bigger set? Okay? So recall tracing. Okay? So we have omega f, and now I'm going to add a mu, measure space. The trace of, first of all, we fixed an A, okay? Let's say A in F. So trace of F on A is this sigma algebra. The sets in F intersected with A, so is a sigma algebra on A. So now restrict mu on A. Restrict mu on A, okay? Because A is already a sigma algebra, so just define nu of A intersection F equals mu of A intersection F for every F in F. This is called the restriction of mu on the trace A, and it is a measure on this smaller measurable space A script A. Now, we passed from omega f mu, we are given a measurable subset of F, and we now create a smaller measure space, A, trace script A, and the restriction of mu on the script A, which we call nu. Sometimes we write nu equals mu restricted on A. So is a measure space. Okay? It's just to complete our program. You know, if you need to pass to a smaller set, you need to make your sigma algebra on it by tracing. And if you are given a measure on the bigger set, just restrict to the subsets which are in the trace sigma algebra. Restrict your measure on the trace sigma algebra. By the same definition, you're not defining it in a weird way. It's just the same definition, right? Mu equals nu on such sets. So that's why we call it just the restriction. Okay? So now you have a new measure space, a smaller measure space. Okay? So you can see, as example, you can see the real line, the Borel sigma algebra, the Lebesgue measure on the whole real line, and the restricted spaces, the interval 0, 1, the Borel sigma algebra on 0, 1, and the Lebesgue measure on 0, 1. Okay? So now we're done with measure spaces. Next is random variables.